Now that I've presented the theory of how to solve a linear system of differential equations, I'd like to move on to a more practical example. In a previous video, we looked at a model of two tanks that contained salt water, where a saltwater solution was being poured into the first tank and a well-mixed solution was draining from the first tank to the second tank. And then again, a well-mixed solution was draining out of the second tank. And that gave us the system of differential equations, ds1 dt equals 1 minus s1 over 25, and ds2 dt equals s1 over 25 minus s2 over 25. And then we wrote that in a matrix vector form, as you see on the right. Now I'm going to present to you two linearly independent solutions to the homogeneous equation. So these are going to be solutions to the equation where I ignore the vector 1, 0. Now, we're going to prove that they are solutions, but the method for obtaining these two solutions will be presented in a future video. So for now, again, I'm going to just assume that this vector 1, 0 does not exist, so I can look at just the homogeneous problem, and I'm going to show that these two functions are solutions. So if I take the derivative of y1 with respect to t, I'm going to get 0 and then negative 1 over 25 e to the minus t over 25. And then if I were to do a times y1, well, that would be the matrix minus 1 over 25, 0, 1 over 25, minus 1 over 25, times the vector 0, and then e to the minus t over 25. And when I do the multiplication, the first row multiplied by this column actually just gives me 0. But then the second row multiplied by the column gives me negative 1 over 25 e to the minus t over 25. And you'll notice that indeed dy1 dt does equal a times y1. So let's look at the second solution, dy2 dt. Okay, for y2, the derivative is going to be minus e to the minus t over 25. And then I'll have to use the product rule on the second part, so that's going to be e to the minus t over 25 minus a t over 25 e to the minus t over 25. So that's dy2 dt. Now let's look at a times y2. Okay, again, we're going to have this same matrix, and we're going to multiply it by my solution. My solution here being 25 e to the minus t over 25, and then t e to the minus t over 25. Let's see what that gives us. When I look at the first row, it looks like I get a minus e to the minus t over 25. And then for the second row, I get e to the minus t over 25 minus t over 25, e to the minus t over 25. And so again, my solution is going to match. Okay, so dy2 dt does equal a times y2. Okay, so now I showed that y1 and y2 are solutions, But now the question is, are they linearly independent? What happens if I take the Wronskian of y1 and y2? Well, that is going to be the determinant of the matrix formed by the columns of y1 and the column of y2. Okay, so taking the determinant, doing the first diagonal, I'm going to get 0, and then minus, I'm going to get 25, and then I'm going to multiply e to the minus t over 25 times e to the minus t over 25. That's going to be e to the minus 2t over 25. And you'll see that that is never 0 because that exponential is actually never 0. Now, it didn't need to be never 0. It just needed to not be 0 for 1 point, one time. But indeed, it's never 0. So the Wronskian is never 0. And so that tells me that y1 and y2 are, in fact, linearly independent. Okay. Now I want to go back to the non-homogeneous problem, and I need to find a particular solution. And in this case, I think I have a slick way to find a particular solution. We just need to find one particular solution. We don't have to find some sort of general form. I just need one particular solution. And so the particular solution I'm interested in finding is actually going to be the equilibrium solution. So what I'm going to do is I'm going to take my my equation, so this is the derivative of S1 and S2 is equal to, and I'm going to write this as, I'm going to write this in not the matrix form, but just in the regular form. So this is 1 minus S1 over 25. And then it's equal to 1 over 25 S1 minus S2. And I'm going to set this equal to 0, 0. Then the first equation says that 1 minus S1 over 25 is equal to 0. And the second equation tells me that 1 over 25 times S1 minus S2 is equal to 0. The first equation says that S1 must be 25, and the second equation says that S2 must be S1. And so Y sub P, which is the vector 25, 25, is our equilibrium solution. So we found a solution so that the derivative of that solution is 0. Now I want to double check, is this actually a solution? Okay, so if I plug in 25 and 25, is that a solution? Well, the derivative y p prime is 0, 0. Okay, now I'm going to look at the right-hand side of the equation. Why don't I call that a done to yp? I'll do it in matrix vector form. So this is negative 1 over 25, 0, 1 over 25, negative 1 over 25, okay, times 25, 25, and then I'm going to add 1, 0. Okay, is that also going to give me 0? Well, when I do the multiplication here, multiplying that first row by the column, I'm going to get negative 1, 0. so the first row times the column gives me a -1. If I do the second row times the column, I will in fact get 0. And then of course I still need to add 1 0. And so yes, a times yp does give me 0, 0. So 25, 25 is indeed a solution to the non-homogeneous problem. And in fact, it's the equilibrium solution. So that was kind of a nice way for us to find a particular solution. So what is the general solution to this problem? Well, y of t is going to be C1 times my first solution. So it's going to be 0 e to the minus t over 25 plus C2 times 25 e to the minus t over 25 t e to the minus t over 25, and then plus 25, 25. Now, what's interesting about this solution is in an earlier video, we saw that solutions approach the equilibrium. Okay, so we saw that if you looked at the limit as t goes to infinity of y of t, that solutions did approach the equilibrium. And this makes sense because if you take the limit as t goes to infinity of these exponentials, each of these exponentials is going to go to 0. And so you're just left with 25, 25. So we did get the behavior that we saw in the previous video where we were looking at solutions approaching the equilibrium. Okay, that gives me a sense that I think that the equilibrium is a stable equilibrium. But again, we'll talk about stability of equilibrium points in a future video.